classic West clock movement, one-day alarm, from around the turn of the century. It is unusual and sought after by collectors today because of the cast pillars and cast arbors in the escapement parts. It cost about 50 cents when it was originally sold, and of course at that period of time it was approximately the wage of a day's labor. The plates are made of brass, and the gear train is made of brass, that is the wheels, and pivots are placed in place within the wheels, and then the arbor is cast from a lead alloy material. West clocks use that technique for near 50 years of manufacturing. This little clock movement has no genuine value as far as timekeeping is concerned, because its error is in the order of several minutes per day at best. Movement built by Seth Thomas around World War I era. This is their famous number 10. It has dual mainsprings, very powerful springs that will power the movement for about 10 days. The reason for the dual mainspring is that this particular movement was used for chart recorders and various industrial devices which required additional motive power. The movement was made with back wind, front wind, center shaft extending through the rear, and several other variations. It was commonly built into what was called locomotive clocks. That is a clock that was used in the cab of steam locomotives in that particular era. It had wide use as an industrial timepiece. This particular specimen has had the dial works replaced on it and several other major repairs. However, it's typical of what you will find in the number 10 Seth Thomas movement. The Lux Company made a similar movement. As a matter of fact, if it does not have the Seth Thomas trademark and you're not familiar with the Seth Thomas number 10 movement, the Lux and the number 10 Seth movement could be confused as being one and the same. There are some subtle differences that separate the two, but in generalities they are very similar. A little one-day carriage clock, if you will. This is about 2 3/4 inches in diameter, in a nickeled case, and approximately 2 inches deep. This little clock was built in Germany, thought to be around the turn of the century. It is a pin lever escapement and was directed to the low end of the American market. The little clock is a nice little unit, runs reasonably well, as most pin lever one-day movements do, and is only valuable as a collector's item. It's not specifically called a carriage clock, but it does have the lifting handle and the feet that it might be readily moved from place to place. It most likely was used as a drum movement in some type of porcelain or otherwise enclosure in its major market. A clock movement destined to be a collector's item. This little unit is about 3 inches in diameter, was built immediately after World War II, and has jewels on the balance staff. It is pin lever and escapement type, has an 8-day mainspring in it, and was directed to use in simple and inexpensive wall clocks. The quartz movement of today has totally displaced the market for this movement, and certainly collectors will seek after this in the immediate years following. The movement is a fairly respectable timekeeper, suitable for keeping time within a couple of minutes a week, and is well built throughout. A Huckabee movement, 4 inches in diameter and about 2 inches deep. This movement was used in mantle clocks around the 1920-1930 era. This is one of the finer movements, and heavily built, nicely cut pinions and gears, and was a very fine clock at that particular time. It is 8-day run, has a platform escapement on its rear plate. This view is from the strike train position of the same Huckabee movement. Looking into the topmost section between the plates, a platform escapement is visible that has been retrofitted into this area. The original platform escapement was on the outside of the rear plate. A rear view of the same Huckabee movement, and a careful look will reveal the screws and the location the original platform escapement set. The escape wheel pinion passed through the slot in the uppermost part of the near plate. This view shows the striker speed control fly in the upper section of the illustration, and the platform escapement in the central area between the plates. This is a modern day escapement, presumably from a yacht movement. A lower view shows the 2 mainspring barrels. The springs in this movement are very strong, very difficult to remove and reinsert into the barrels. A little 8-day German movement built immediately after World War II. This particular movement has stopworks on the mainspring, and was directed to small, inexpensive hanging wall clocks. Though the movement looks nice, it is not a very good timekeeper, and not very well powered. Consequently, the smallest amount of drying oil, dust, or whatnot sent this particular movement to the trash can. This is the rear view of a number 10 Seth Thomas movement with rear wind and built for an industrial chart drive. It is similar to the one that we looked at earlier in this film, but the other side, the operating side, has no dial works. Movement front side of the same movement. This shows the drive shaft, which was coupled to a chart drive with a 1-day chart disc about 15 inches in diameter. The disc was recorded with a pair of ink pens. This tool is an English Turns, thought to be 200 to 300 years old. It is mounted in a modern day drill press vise with a crank and drive wheel at the rear mounted on the same vise. This setup brings the combination of tools to what is known as the English clockmaker's throw, or approximately thereof. The lathe, or the turns, is the forerunner of the modern day engine lathe, and is a dead center lathe capable of a very high degree of accuracy. This one has been extensively used, as indicated by the wear on the tool rest and various other parts. Here we're looking at the turns as it was used by the English watchmaker. The left lower end was mounted in the bench vise, and the little hook at the extreme lower left was used to hang the bow, which was used to drive the work between centers. This is equipped with a female center on the left end, a male center on the right end, and a ferrule for powering a driving dog is on the right end of the left spindle. We're looking at the tool set that's used with the English turns. This has a large variety of runners. Runners is a term used for the various centers that's used to support the work. The ferrules, or what is called driving dogs today, and many other devices used for making balance staffs, repivoting staffs, and small clock wheels. The disc in the right foreground has a variety of cup-shaped holes that is used to support wheels as their centers are drilled to take replacement pivots. That's the tool that is primarily used for repivoting large watches and small clocks. The humble file is the most basic tool used by the clockmaker today. This group of files, which numbers about 65, is only a small portion of what a clockmaker may use in the manufacture of replacement parts. The file, as basic as it is one of the most important tools of the clockmaker's tool set. Rotary files and stones are an important supplement to the hand file. Many uses of the rotary files in a small handheld power tool, or in the chuck of a drill press, or the chuck of a lathe, performs many time-saving chores. Watchmaker staking set is probably more used by the clockmaker than by the watchmaker. However, it's used in a different role. To the clockmaker, it's primarily used for riveting, that is, small rivets and eyelets, cutting thin stock, and piercing holes in material that is too thin to be readily handled with a drill press or a drill in the lathe. A variety of sizes of punches, generally larger than watchmaker punches, is needed. There is a never-ending need for larger punches in the clock shop. These two blocks of punches represent a variety that is used essentially every day in clockwork. The clockmaker's punch has little value without a suitable anvil. Anvils, commonly called bench blocks, come in a variety of sizes, and the need seems to be endless. It seems to matter not how many hole sizes that you have available, there is always one more that's needed. This group here is representative of what may be found in the typical clock shop. Several of these are handmade for specific purposes. Every clockmaker has a desire for facilities to make wheels and pinions, but with the equipment to do this job comes the plague of where does the index plates come from. This group of index plates is approximately 100 in count, yet it does not cover nearly the wheel tooth counts that we encounter in daily clockwork. These plates were made over a period of many years, many of them copied from gears in clocks that were in the shop for repair. And even today, if a gear comes in a clock that has a tooth count for which I do not have an index plate, I copy the count onto an index plate before the clock is returned to the customer. These plates will probably handle 90% of all the tooth counts of gears normally encountered, but the odd one, for which there is no plate, is the priceless job that we need in our shop. The question often asked is what lathes should be used by the clockmaker. Actually, there are many lathes that perform well for the clockmaker, but all in all, a good strong watchmaker's lathe is quite suitable, though a little on the small side. This illustration shows a G. Boley lathe, possibly 50 years old, that is outfitted for a certain type of clockwork. The things that make this particular setup desirable is, number one, it's mounted on a base. The base, which can be moved about such that the work is in full view. Ordinarily, a job of the type that we're showing here should be viewed from this direction such that you can look directly into the tool bit and the work that's being carried on. This lathe mounts on a base with a constant speed motor. This motor is about 1/10 horsepower, considerably slower speed than the watchmaker's lathe motor, has a larger pulley to the rear such that there is not a particular problem with the belt slippage, and it's generally driven onto the large pulley only. This gives you lower speed with higher torque and a constant speed which is needed for the heavier machine work. In addition, this machine has the tool slide, the 3-deck tool slide. It has a bezel chuck, which at this point is holding the great wheel of a small clock. Insertable tool bits that are held in the tool post, a micrometer barrel for a stop to the rear, and a dial gauge for the longitudinal feed. It's often convenient to operate the lathe from the vantage point that we see in this photograph. The tool bit at the pencil point should be in full view at all times, and by turning the lathe at this angle we look in really to the rear side of the work, and this gives a distinct advantage in observing your micrometer stop, but we lose the advantage of seeing the dial gauge on the front side. However, this dial gauge may be rotated, and with an overlook we can see into the top of that particular instrument. This particular setup is holding the great wheel by its teeth in a 6-jaw bezel chuck. This gives us adequate protection for the teeth, and if we cut carefully, we can cut from this pivot by the support of the wheel. However, the wheel spokes renders this setup just a bit springy, and it's necessary to have an extremely sharp tool for this work. This view shows us the azimuth adjustment on the tool slide. By releasing this screw, we can turn the tool slide for making tapered or angular cuts. The micrometer barrel is a stop for the tool slide. By adjusting this stop at the position the last cut was made, then dial in the additional cut and pull against the stop, gives us the ability to make cuts as small as 1/10 of a millimeter with great ease, and with some difficulty cuts as small as 1/100 of a millimeter may be made. This dial gauge controls cuts as small as 1/1000th of an inch. The gauge may be set to 0 and the cut measured from that point. When the gauge is not used, it's simply slipped off of the instrument. Here we recognize the lathe as simply a basic watchmaker's lathe. This is mounted on the base, and the power switch is in the right frontmost leg. The motor is a constant speed motor, and this is the draw bolt for the tool holder, tool rest, slide, or various other fixtures that might be used. The spindle diameter in this particular lathe is the Webster Whitcomb size. We're looking at a commercial tool slide for a watchmaker's lathe. We see the tool holder that holds 3/16 inch square bits, the horizontal feed, the longitudinal feed, and an auxiliary horizontal feed. Here we have the micrometer tail stop, slide stop, not tail stop, and that stop is adapted to the particular tool holder by this block that has been added to the slide. This is the micrometer tool holder, a Starrett instrument. Turning the slide around, we take a look and we see the location, the block, for installing the longitudinal tool holder. Not tool holder, the tool stop. In this particular case, this slide is too close to the holder to mount this at the moment. Backing the slide off will correct that situation. Looking further, this is the bezel chuck, which has 6 jaws, and these jaws have stepped inserts and can hold a variety of types of wheels on the OD, and the steps at this point can hold a variety of sizes of rings on the ID. This is a very useful chuck to the clockmaker. Here we have about 2 dozen collets, or wire chucks as commonly called in the watchmaker's trade, and a pair of 3-jaw chucks. These collets are sized in common sizes that are used in clocks, and reduces the number of collets required by a substantial economic savings. The some 25 or 30 collets that's here range from about number 5, a metric number 5 collet, up to 1/4 inch in the largest size that we have right here. However, in the watchmaker's lathe, a number 46 or a 47 collet is the largest size that has a through bore equal to its mouth size. These larger collets, such as this, do not have a through bore equal to the mouth diameter. These are approximately 3/16 of an inch deep. These chucks, 3-jaw chucks, have a through bore of about 3/16 of an inch in each of those. This collet group here is Mosley number 2 size. This is a Webster Whitcomb size spindle, and this one is a Mosley number 2. This one is made by Boley and Lennon. This one is Swiss made. These 2 chucks here are small wheel chucks. This block of collets is the size commonly known as Magnus Elect, commonly used in the lathes built by the Derbyshire Company, as well as the Derbyshire Micromill. Some 65 of these, and they are ranged over Brown and Sharp gauge sizes, metric sizes, preferred English dimension sizes, and some that have been bored for special purposes. These are used in the little Derbyshire micromill and is a good selection for most anything that is needed in that mill. Let's speak to special tools used for clockmaking. Having the basic lathe and the tool slide is just the beginning of the need of special tools and fixtures. Let's look at these by function more than the detailed shape. As we look, this group here is handheld gravers as used with the watchmaker's lathe. These are very, very useful in the smallest of work. As we look at this tool block here, each of these tools, of the bits, are double-ended so that serve two purposes. For instance, we have here boring bars, we have cut-off tools, we have square end, round nose, and a variety of types of tools there. We have the Allen wrenches that fit the some of the tool post. These are keys for tool post and for lathe chucks. As we look at this is a 1/8 inch square piece of tool stock, ground as a boring bar on one end, as a V-cutter on the other. This tool here, a little larger, it's ground as a V-cutter on both ends. This is a double-ended boring bar here. This is boring on one end and turning on another, and so on. As we look a little further, we pick up a tool of this type. This particular tool is held in a boring bar tool post, but in its tip it has a rotary file. This makes an admirable boring bar for any hole that rotary file will pass through. This is tool post raising devices to hold round tools, such as the combination right here. And these instruments here are a variety of drawbar, drawbolt spacers. Not every drawbar and every tool that you will have will work out to fit the spindle of your lathe, particularly if you have a multiplicity of lathes. And these spacers are used to cope with that problem. This particular little boring bar here, and it's hardly detectable in the end, holds a dental burr. That dental burr is used as a boring tool for the smallest of holes. A collet can be bored to a depth of almost 1/4 of an inch with that tool, and still the idea of that collet being no more than a millimeter in diameter or less. Center drills, more tool post spacers. This is a carbide tool bit here. The holder is not shown that it's used in, but this particular cutter has 6 surfaces on it. It's a triangle, can be turned upside down, and serves as 6 cutters. This particular tool here, and possibly we can see the tip of it, is made to cut a gear cutter. You see that the tool is the little angled steel music wire that passes through the end. Passes at an angle, ground flat on top. That gives us an elliptical shape, gives us a pure elliptical shaped cut that we need for the formation of some gear cutter tooth profiles. This is just a few of the tools that's used in lathes. Probably a good selection is 2 or 3 or 4 or 5 times that number of tools. Most have to be made on the spot at some time for a particular purpose. Like punches and files, the clockmaker never has enough drills. We have here a drill index for sizes 1 to 60, and here sizes 61 to 80. This is by far the most important group of drills that the clockmaker will ever use. You may add, in addition to this, a similar index in preferred fraction sizes from 1/32 or possibly 1/16 up through 1/4 inch. And to improve the set, you may add A through Z drills. This is an expensive outlay of drills when you have an index of all the sizes, and time will come that every one of them must be used, and there will be other drills that you will need also. I use commercial mascot bits for the smaller sizes to supplement the sizes that we've just mentioned. The drill situation is such that you would do well to buy what is called screw machine drills. A screw machine drill has a very short flute, has a very short chucking shank. Consequently, it does not walk as badly when you begin to start the drill. It's made for specific purpose of drilling without having a pilot hole or a center to begin with, and that's helpful in clockmaking, particularly if you're drilling in the tailstock with the watchmaker's lathe, because you're limited on the number of inches between centers on that lathe, and a drill bit of extra length uses up that space that may well be needed for something else. Also, the term jobber's length drill bits, and that is what this pack of bits here is a longer bit, much as you find in most hardware stores. Most drills that you find in hardware stores and tool shops are what is called jobber's length bits. Like taps and dies, like punches, like files, there seems to never be enough of what we need. We're looking here at a screw pitch gauge, a die holder, die, and a die, and a group of dies. These dies are in the 3/4 inch diameter and range in size from a number 1032 down to 0.80. I have all sizes here of screw machine threads, plus our machine screw threads, plus several other finer pitches. There are no metric pitches here, and one of the problems in nuts and screws in clocks is that many clock manufacturers had their own standards for taps and dies years ago. Consequently, having all known sizes of metric and all known sizes of English threads does not really solve the problem. The time will come when it will be necessary to either enlarge a hole and make a new screw, or reduce the diameter of a tenon and make a new nut. This selection here pretty well meets clockmakers' needs. This selection of taps covers the range of the dies that we looked at in the previous picture. There are several taps of each size in this group, and some are plug taps, some are bottoming taps, some are starting taps. But as taps become used and worn, their ends can be ground off and bottoming taps made from plug taps. Oftentimes, if a tap is broken on the tip end, it can be cut back and used as a bottoming tap. So be careful with the taps. They're expensive. If you size the holes carefully, and the lettered size drills are needed to do that, if you size them carefully, they will last many, many years. This is a metric set of taps and dies. There are 2 or 3 taps for each die, and the size ranges from 0.39 millimeter, which is about 15 thousandths of an inch, up to 1.75 millimeter, which is about 69 thousandths of an inch. Here again, as these sizes become smaller, it is more important to size the hole that is being tapped, or the body of the tang that is being threaded. Size it correctly, because a broken tap may spoil a piece of clockwork that cannot be recovered. Also, a broken a piece of stock in one of the dies is a trouble that is really unnecessary. Generally speaking, taps of this size should be turned with your fingers, not with a wrench or a tool. The smallest tap here can easily be twisted off between the thumb and the forefinger. The larger size taps are pretty much safe with anything that you can torque between the naked fingers. So the rule of the thumb is to use the finger and the thumb, and don't break the taps. The wooden handle has a chuck in the end of it to hold the dies. This is a good little metric set for clockwork as well as watchwork. While the camera's in range, let's look at the clock that I have at the end of my workbench. This is a jewelry store regulator which I constructed about 1 year ago. This is a 60 beat movement, double weight drive, maintaining power by the fact that 2 weights drive into a common train, is capable of about 10 or 15 seconds a month, plus or minus accuracy. It has a wood stick pendulum, which is not fine by any means. The case is made of solid oak, with the exception of the back, which is a plywood back. The dial is made of mylar, and the numerals and the markings are silver deposited in ultraviolet etching, which was made photographically from the artwork that I made up for the dial. I built 2 of these clocks beginning in December the 2nd of 1965, finished, no, I'm sorry, that was 1966, and I finished in April of 1967. The 2 are identical. All parts in the 2 clocks are interchangeable. These were built for my family, children, and grandchildren as family heirlooms. Now let's look down the clock. The clock is sitting on the floor at the moment. Up until not too many days ago, I had a pair of them sitting here side by side. They're identical in every respect. I have a full set of technical drawings on them, all scale drawn, and dimensional detail such that replacement parts could be made without ever seeing the movement that they're to go into. If you'll notice, in the right lower corner, you can see a shadow right in the right lower corner of this door. That is a cardboard tube that holds a roll of the technical drawings for this particular clock. There is a little over 100 pages of those drawings, and there is a compartment behind the dial for those to be placed in. It happens that when I put the dial on the last time, I neglected to put the prints with the movement. The reason for this situation is that an antique clock that was built 100 or 200 years ago would be worth several times its face value if it had the hand-drawn prints and all the details of the workman that built the clock. Let's take another look. There are some objects that's not related to the clock that's sitting on top of it. I also noticed some reflections on the glass from the door. The weights, the position of the weights as they are today, this is Saturday. It was wound on Sunday, 2 Sundays ago. That says that those weights are down 13 days since the clock was wound. 2 of these, identical, are made for family heirlooms for my children and grandchildren. Turning the camera around in the opposite side of the room, you see my shop regulator. This regulator was built in 1966, about 21 years ago, and has a very large movement, as you can see through the opening in the dial. The plates are aluminum with bronze bushings in each of the pivot holes. It has a unique escapement which I developed, and to my knowledge there is no other escapement ever been published of this type. I call it a shuttle escapement. There's a shuttle that passes through the escape wheel, and the escapement pallets are exactly opposite each other on the wheel. The shuttle is suspended on 2 suspension springs, and then it has another device that has the analogy of a crutch to get from the shuttle out through the back and down to the crutch on the pendulum rod. This movement has turned out to be remarkably good for a free-running movement, particularly as a home-built movement. It requires very, very little attention as far as cleaning and oiling is concerned. The pendulum weighs 21 pounds. It's made of 3 brass tubes, 2 of which are filled with lead, the center one being hollow. The pendulum rod is made from Carpenter 37 Invar, that is a temperature compensated material. There is a bit of steel in the suspension spring and the suspension. The temperature compensation is a little less than perfect, but the rate is very, very good. Notice in the upper left section of the dial you see a little blue splash in that area. That is from a blue ink pen, and the words there say set February the 5th, 1966. Today is November the 21st. I'm sorry, I think I told that number wrong. Set February the 5th, 1986. 1986. Today is November the 21st, 1987. Or about, I suppose that's about 21 months since the clock has been set. I wind this on Sunday mornings, and I clock the era against WWV and plot that era continuously. Last Sunday morning, when I wound the clock, I was 113 seconds slow, and that is an average era, I believe, of something like 6 seconds a month over that period of time. The weights, as you see them now, are 6 days down from full wound. I will wind them tomorrow morning. They fall about 2 3/4 inches per day. This clock has maintaining power. It has a common hoist drum for the 2 weights. One key lifts both weights simultaneously. A stored energy mechanism in it gives it the maintaining power so that it can be wound without losing any escapement time. Now let's look down the clock. As we look down, we see the reflection on the glass is the first thing I notice, but the nameplates, Shuttle Escapement Regulator by J.M. Huckabee, November 1966. That's when the clock was built. You see that the pendulum rod is very small, namely 1/4 of an inch in diameter of the Carpenter Invar steel. We come down, the pendulum is ornate in nature, and now you can see the thing that I was speaking of, made of the 3 cylinders, 2 of which, the outside 2, are filled with lead, the center one being hollow. The total weight of the pendulum is in round numbers 21 pounds. This particular movement was made to operate with a very minimum of pendulum swing. It swings about 1 1/8 degree each side of plumb. The escapement point on the escapement mechanism has at 3/4 of a degree each side of plumb, so I have an overshoot of about 50% over the nominal swing. This movement is now a little over 20 years old, and it has been cleaned 3 times in that period of time. The last cleaning being on February 5th of last year, when I set it running and started it again. The arrangement is made such that when the movement is removed from the case, the pendulum remains hanging in the case. Consequently, the movement can be removed, cleaned, oiled, and replaced without disturbing the rate of the pendulum. This case is made of cherry. It has a beveled edge, cut glass door, both upper and lower doors. The red finish that's on the case, it's not too visible in this picture, but the red is the natural color of the cherry. This case was rubbed down with a mixture of beeswax dissolved in boiled linseed oil. That's the only finish that it has on it. This is the shop regulator, and it is one of 5 clocks that I have built over a number of years. Moving over next door, we find another clock, a hanging wall regulator, which is sitting on the floor. This particular clock, the legend on the dial says International Time Recorder Company of Endicott, New York. This was a master time clock and program system. The program machine has been removed in the distant years past. I worked for IBM almost 40 years. The clock that you're looking at here, according to the serial numbers on it and the IBM records, was built in 1928. It was supplied to Central High School in Jackson, Mississippi. It ran there until the end of World War II. It was then removed to Lanier High School, another school in Jackson, Mississippi. Around 1958, that clock was replaced with a new unit, and when it was, I purchased this specimen. If we look down this, we find, as we look down it, it has a wood stick pendulum. Looking a little further, you can see the markings where the program machine once sat. You see a double pole knife switch in the right section of the illustration. Down a little further, a relay that no longer exists. And down in the bottom, the scale on the pendulum. It's swinging about 3.5 degrees each side of plumb at the moment. That particular pendulum ball weighs about 7 pounds. It is electrically wound. Each minute, an impulse ratchets the mainspring up another step, and at the end of each hour there is 20 additional steps that's provided in case there has been a short power failure in the meantime. There is an overflow mechanism such that the spring does not overwind. It is the same concept that we have in mechanical wound, in automatic wound wristwatches. That is, overwinding does not overwind the spring. This particular clock is capable of about plus or minus 30 seconds a month. The movement is very heavy, very fine made. The plates are made of 1/8 inch thick brass. The wheels are made of brass that's 92 thousandths of an inch thick, and all the brass work in it is gold plated. All of the steel work in it, that is the arbors and pinions, are highly polished, and all of the other steel work such as pillars, etc., are blued. This movement is not extraordinarily fine as a timekeeper, but it is extremely fine as a durable operating mechanism. The case is solid oak, has locks at top and the bottom of the door. Let's talk about the tools to make gear cutters. We're looking here at gear cutters, oftentimes called gear hobs, but these are really profiled saws. If we take a look here, this is about the size of a 25-cent coin. The teeth on this have relief, and when they're sharpened, all that's necessary is to grind on the foredge of the teeth, and that restores the cutter to like new cutting condition. This particular cutter here is labeled D.14-16, and there is a second set of numerals on here that says M.0.65. The interpretation of this numbering system is D is for dents, namely teeth, and this cutter is suitable for making a pinion with 14, 15, or 16 teeth. The size on it is in the module system, and the M .0.65 means 0.65 millimeter module. That is a little smaller tooth profile than what is found in the typical 8-day kitchen clock. This particular cutter here looks similar to the one that we just looked at, has a fewer teeth, and it's to cut a pinion of 12 or 13 teeth, and is in 0.8 module. That is the cutter that you would use in most kitchen clocks, that is in the great wheel of the kitchen clock. This particular cutter here is to cut an 8-tooth pinion in the 0.8 module, has been sharpened many times. You see the teeth on this are narrower in this particular view than original. That cutter's probably been sharpened more than 20 times in its life. This little cutter here is a handmade unit made of a piece of spring steel, made of the steel stock with its spring hard, and it was ground to profile, and the teeth were ground in place on it. This cutter was used to cut the crown wheel of a small French carriage clock. As we look a little further, this cutter here is one that is handmade for a particular profile in a large French clock in the great wheel, and that particular clock was thought to be about 150 years old. I made this cutter from a piece of a mill file. The file was placed in the fireplace, and after the ashes cooled, it was annealed. I made the cutter, turned it out in the rough, then ground the teeth to shape. That cutter was made to make one gear and has never made another. Was made about 20 years ago. This particular cutter here is made in accordance with the instruction of the Levin book of many years ago. These teeth are somewhat springy, as the holes and the relief pattern here would show. Though I've made many gears with it, it is not a type of cutter that I would make at some future date. As we look here, we find there's something in the order of 50, 60, or possibly 70 cutters that I have, and among these, it's possible, I once did a little thought on the profile and tooth counts that could be made with this group of cutters. It probably exceeds 600 different pinion profiles, gear profiles, and tooth counts that can be cut with this group. These cutters, the commercial ones, I had made in Switzerland. They were custom made to drawings that I sent to Switzerland some 20 or 25 years ago. Most of these cutters have been used many times, and possibly there's one here somewhere that has never been used. Now let's look a little further at what gears, wheels, if you will, and pinions look like when they're first constructed. These wheels are all commercially made. This is overrun from commercial clock manufacturing business. These blanks are cut out on punch press from sheet stock, stacked into a group, and then machined in stacks of probably 50 or more pieces. This particular one here has a 64 on it. That says that has 64 teeth. These were bought as a manufacturer's overrun. The particular reason for buying it is not that I expected to ever find a clock movement or a need for these, but that I might find some odd or unusual tooth counts. If you have a gear that has good teeth, is well indexed, well machined, this can be set up in your gear cutting system, and the tooth count can be transferred to index plates. The index plates we saw earlier in the this particular film. This in this group of some 20 or 30 of these that I purchased at one time, I found 2 or 3 counts that I made index plates from that I never had before. Now let's look at some pinions. This is a group of pinions that is from an overrun from a clock manufacturer. They are nicely made, they're moderately hard, and the probability of ever fitting one of these to a clock need is extremely remote. It is really folly to purchase random wheels or random pinions thinking that you will ever use them. The purpose in purchasing these is that I do quite a bit of clock building, generally making the arbors and the pinions and the wheels from raw material stock. But with a selection of pinions of this particular type and wheels that we might have like this, it would be feasible to build a clock of some special design and save a considerable amount of work in so doing. The greatest use that I find for these particular pinions is that if I need a pinion, if I can approximate the length, diameter, pivots, tooth counts, whatnot, that I can set this in the lathe, rework the arbor, recut the teeth with the appropriate profile and to the appropriate diameter, and fit this into a clock more quickly than I could do that from blanking it out from raw material stock. So that's one of the ways that random wheels, pinions might be used. Generally speaking, though, it is not probable that you could go from a selection like this to a usable wheel or a usable pinion directly in a timepiece. Let's go through a little routine with a depthing tool. Let's imagine that we have this clock plate and a gear and the wheel that's associated with the next pinion, and that these are located in these two positions on this plate. Now, our object will be to locate a pinion that we can replace in the next wheel. So let's look at this and see how we use the depthing tool for that type of job. This being the depthing tool, the clockmaker's depthing tool, this is somewhat of a medium size, not as large as is needed with the larger clocks. It has a pair of runners here. This is male tips, female tips, pair of females here, pair of males here. These runners can be exchanged in ends as is needed for a particular job, and our objective here will be to test a pinion that we have picked from a random group of pinions and see if it would be suitable to work into this particular movement. The first thing is to find the center distance. This adjustment here sets the center distance. We'll look at that to the movement plate. We're a little too wide here, so we dial in the size that we need to test our wheel and pinion. That is approximately right, and that's suitable at this point in time. Now, it's well if we measure the center distances on both plates. On many movements, we'll find that there are slight differences in the two plates, and it is prudent to check that distance on both plates. Now, I picked a pinion from the random group that we looked at previously to see whether or not this pinion and arbor might be used in the wheel that we're speaking of. So let's load these into our depthing tool. We'll place this pinion, its centers, between the female ends of the runners. We want this so that it turns completely free, absolutely no bind and no slack. It's important that we do that. Now we load in our wheel and do this likewise, keeping these 2 points in their position that we use for the measurement. Slide this runner in place and tighten this up, and now let's see what we have in the way of a working system. As I turn this, I find that this feels a bit tight. There's backlash between the wheel teeth and the pinion teeth, so this may be a pivot tightness that we're talking about. So let's try adjusting that. No, we still can't make it. Let's widen this space slightly. We loosen somewhat. We try a little more. Now I find that we're approximately right. If I turn this runner, it turns the pinion and turns the wheel, and this is turning freely. Let's see if it rolls if we use the wheel as a driver. I can still feel some tight spots there. You can probably see that the pinion is not turning smoothly. Let's increase the center distance slightly again. I still feel that it is not totally free. We'll try a little more center distance. Now I'm approximately right. You can see the pinion rolls nicely. But one of the things I'm experiencing is that the wheel is slightly out of round. Or is it the pinion? It may be a little of both, because there's some tight spots at about one spot around the wheel. There seems to be a tight spot at about one position around the pinion. So let's turn again. We seem to be all right there. And let's check for our slack. And we turn nicely there. And we would assume here that we approximately have a match that can be used. Let's look again. There's still a slight bit of bind in this. Looking between the teeth, looking down between here, let's see what the backlash looks like. We have considerable backlash that we can see there. which says the center distances are appropriate for these, and let's see the end play. The end play in this pinion is absolutely zero at that point. Let's increase that slightly. Didn't make it. Try again. And we have a slight amount of end play. Now it turns very freely. Very, very, very free. Possibly this can be seen in the photograph. Let's try diminishing the center distance slightly and see if we still have the freedom. And we do. And some more. And the thing that we're doing there is trying increasing and decreasing the center distance. At that point, I'm too close. At that point, I feel very good, and very good at this point. Small amount of backlash. So with the depthing tool, we have found the center distance that can work with this pinion and this wheel combination. Now let's try transferring that to our plate. Let's see if we can sit right here. And what do I find? I find that the center distance on the depthing tool is ever so slightly wider, probably as much as 2 to 5 thousandths of an inch wider than the distance between the holes. Now the question is it possible for me to machine up this pinion arbor to fit the plate, stake the wheel that belongs with it onto this, and use it? The question I would answer as a yes. I would answer the question yes. And let's look and see why that we have this answer. Looking at this plate, going up the gear train, we have gear, gear, gear. Now, we're dealing with this distance right here. We have this one here. Now, this says that we cannot adjust the position of this pivot on this axis without increasing or decreasing this distance. Also, an adjustment to compensate this would cause an error here. We can move that pivot on this axis one way or the other and find a place that we could gain a little more distance. I believe that in a repair that we should machine this pinion up, set the wheel on it, and then go into this pivot hole that we're going to use, fit a fairly large bushing in there. A bushing that is in the order of 1/8 of an inch in diameter. When we have that bushing fitted, then we will drill the hole off center in that bushing after it is placed in there. By that, we can take the measurement. From the depthing tool, we can locate this on one axis. We can also take the dimension from here with the depthing tool, with a second depthing tool, and incidentally a watchmaker size depthing tool is suitable for that closer measurement. So we have two tools, each with the appropriate depthing. Then we can locate that spot by striking an arc against the pivots, and where the arc crosses we can drill that bushing. And we find that we could fit that pinion into this and make a suitable running movement. Now this is one of the things that you can use the depthing tool for. The thing that I use it for mostly is working on escape wheels and the escapement pallet. You set the pallet and the escape wheel in here, take the distance from the movement, and now you have the escapement out where that you can look at in its best form. So this is one of the uses that we find with the depthing tool, and it's a very useful tool. The tools are expensive. It's difficult to even locate one that can be purchased, even though the price is high. But you will find that it is a very valuable tool in the clock. Let's look at a mainspring in a typical 8-day clock. This spring is the terror of the clockmaker. Everyone has the problem as a beginning clockmaker, is how do I get this spring into the clock movement? And rightly so, because the spring is larger than the movement that it's to go into. This is a spring typical as would be removed from a clock. It has a gum on the surface. It's sticky. You can see the bright spots from the wear. If the spring is wound tightly with this gum residue on it, the turns become glued together. Consequently, this cuts off the power to the escapement train or the striker train, and the movement stops. So it's necessary that the spring be cleaned carefully, all the gum residue removed, and in the process then lubricated with a non-drying lubricant. Now let's look at the mainspring winder. The simplest appearing tool, and one of the most useful tools in the shop, because we cannot survive without a mainspring winder. This is probably the most desirable type of mainspring winder to have for open springs of this general type. So let's take a look. Let's get this spring ready to go into the clock movement. First, we use the great wheel from the movement that we are working on. We look at the great wheel from the side that has the click on this. We will be lifting the click spring so that when this arbor is rotated, that the click will disengage. At other times we will have the spring on top of the click so that it will be functional as in the clock. First thing, ratchet wheel down goes into the pocket on the winder. Ratchet wheel down into the pocket. We take the clamp, and the purpose of the clamp is to secure the great wheel to the winding tool. Tighten the key tightly, wing nut, and the ratchet is inside. We have it accessible through this port, and we're ready to wind the mainspring. At this point, we inspect the hook on the mainspring and the direction of rotation. We're using a let-down key, bench let-down key. There's a variety of types of these let-down tools. We select the end that fits the arbor, and that becomes a winding device to wind up or to let down the spring. Now let's look at the hook on the arbor. The hook at this point, and we look at the direction of the hook, and we find that this particular hook is pointing around clockwise. That means the spring must be wound in this direction, and that the outer end of the spring goes over the stud. Slipped on like this, going around in the clockwise direction. We take the bulk of the spring and sit this over the arbor. Now, the inner turn of this spring must be formed with a long nose plier such that it will hook up with the arbor as we begin the winding operation. You may find for safety reasons to use a glove when doing this, but unless you have a tight kid-skin glove, it is probably more difficult to use than with the bare hands. The edges of the springs are polished, and though they can cut, if you're careful, there is not a particular problem. We now take the winder. We begin winding this just as if it were in the clock movement itself. We must constantly keep the spring flat against the winder. This will want to bulge out like this, and the spring fall off, so we must hold this inward all the time we're winding. Hold it in the hand and begin to wind. Change hands here to possibly improve the view a little, and we're winding the spring. Another view. The spring has not been cleaned. We're doing this for illustration. Continue to wind. This can equally well be done with a winding key, using the same precaution, being sure that the detent or the click seats before we release the key each time. Continue to wind and lift the spring and see that it get back in the view here again. Be sure the spring remains flat against the winder. Continue. Here is the condition where the spring wants to get out of the winder. That must be held down. There, again, we have the condition where the spring attempts to get out of the winder, right in this area. Hold it such. Continue to wind. About this point, let's try the mainspring clamp. We have this wound about as it would be in 4 or 5 days of run time. You see the tendency for the spring to bulge and attempt to get away. Never turn it loose there. Let's try our clamp. And that's just about the right point. This clamp is to hold the spring in place. Now, this is dropped on. The next step is to let the mainspring down. We turn this around. The click is latched securely at this particular point. We reach in with a tweezer and lift the spring off of the click, holding this tightly in the fist so it cannot get away. We wind up a little and let the spring down. It was not intended to let it down that rapidly, though we did. And we're inside the clamp, and at this point the spring is completely down inside the clamp. Now let's see what we do about that. Remove this. Spring is fully wound. Back turn the arbor. We have the spring in the clamp. Now let's think about some pitfalls of this. First, we want to be very sure that the clamp is centered on the spring and it will not slip out. The second thing, we want to look at the overhang on the end, right here. This is probably a little too long to conveniently assemble into the movement because we have this type of force here. That says that the spring clamp should overlap up to about this point. That could have been corrected and established while we had this in the winder. Let's look at it again. Let's say we want to move that position. We latch up the arbor. We put on the winder, and again we clamp the wheel in place. Alright, we're ready to relocate the clamp on the mainspring. Back goes the spring on the detent, on the click, and we wind until the spring begins to slack the clamp. Let's see what we have here. Not enough yet. A little more. Let's try that. No. A little more. And again. No. And again. There we are. We can rotate the spring clamp to bring its end near the end of the spring. We're looking at the end of the spring. We're looking at the end of the clamp. Now the situation is to let the spring down again. Lift the click spring. And try our key. Now we're letting down slowly using this egg-shaped handle to let the spring off slowly, as I should have done a little earlier in the picture. Now let's lift off and see what we have. Here we go, ready to assemble into the clock. The spring is not clean, of course, but this is how that it would look. We find here that the end of the clamp is very close to the end of the spring. If we are replacing, or for some reason we want this removed from the arbor, we must do this. If I pull out, I may empty this mainspring in my hands. So reach inside with the thumb, hold the spring down, rotate the arbor to unhook the hook, and I'm having a little trouble unhooking the hook here. There we go. Be sure that the spring is held from both sides while you're pulling that arbor out. As we look at it here, the clamp is not centered on the spring. We can correct that a bit here for a little more safety with our fingers. And once you have become completely familiar with mainsprings, here's a trick that you can do, but this is one that you would have to be very careful with. If you desire to have the spring out of the clamp, as the case is when it's removed from the clock and you wish to clean it, the thing to do is to catch it like this. Two sides, thumbs against the clamp. And in a place where there's plenty of space, preferably against the floor, take this and push quickly down with both thumbs. That empties the spring from the clamp. Now, in so doing, it will suddenly get possibly 2 feet in diameter, and it will be necessary to not have the hands under it. Hold the clamp only, thumbs here, pop this out. You can pop that spring out of the clamp. It jumps with a bit of violence and noise, but you can dump it into the floor, and it is something that you can readily do and is a time saver. Now let's look at this spring. I thought as we were looking at it and it's dirty that the spring was perfectly good. But let me find a spot here that I just discovered. I don't know if this can be seen in the picture, but right here, right at this spot in the spring, is a sharp bend. Let's see if we can find that. Not very well in the picture, but we notice there's a space. There's a space as we come around between these two turns in the spring. Right at that point, I can feel a rough spot with a pencil. I can see that there's a slight bend in that. What I suspect that is there is an incipient crack where it's fixing to break. Now, I'll dump this spring and we'll take a look at it and see what we have here. I don't have the camera where I can show you the dump of the spring, but I will do that, and in a moment we'll look again. So a bit of patience and we'll see what that place is in the spring. The time lapse, since the camera was turned off, has been less than 20 seconds. Let's see if we can locate that particular flaw that's in the spring. We'll look around the edges. I'm feeling the edge of the spring through the turns to locate the particular place, and as yet we haven't found it. The spring got looped around and needs to be straightened there. And I'm amazed that it was so vivid when it was wound, yet I don't find it at this point. Considerable amount of gum on this spring, and it's highly improbable that it would run satisfactorily in a movement without being cleaned. This is one that I picked up under the bench that's quite a number of years old, and has been removed from a clock for some reason that I don't recall. But I'm at a total loss to find the spot that we were looking for in this spring that I thought that was an incipient crack. The situation was so vivid previously that I was certain that we would find a crack there, and I do not. Let's wind it up and look at it again. Let's look at this process again. We place the spring back on the click. That's the click spring. Ratchet down. Place on the wheel clamp. Tighten it up. We want to wind in the clockwise direction, means the spring is loaded on this way, and on the arbor. You may find that loading this on the arbor is easier if we do that before we hook up the outside end. Now, if this is the opposite spring in let's say that this is the time spring, and we go to handle the striker spring that's wound in the opposite direction, the spring would simply be turned over the other way and hooked in the opposite direction. But the direction of the ratchet on the grate wheel tells us which way that we must wind it. Wind up, and we'll see if we can find the you note that I continue to hold this assembly in the fist as if it were a baseball or something that we are holding quite tightly. That's to keep the spring from jumping out of the winding tool. Oddly enough, I do not see the flaw that I imagined earlier. Let's see what the clamp looks like. We're wound to the point that with a little urgency, I can place the clamp on the spring. At this point, it will not drop on, but with a little urgency, the clamp can be placed on the spring like that. That winding to that level makes it a little easier to handle. Let's lift the click and let the spring down in the clamp. All right, spring's down in the clamp. Clamp is safely on the spring. And I believe that the imagined defect that I had in this, now I'm looking for a rough spot on this, and I don't find it. I believe that there was probably a little piece of foreign matter between the spring that spaced that off and gave me the illusion of an incipient crack in the spring. Here we are. If the spring had been cleaned as we had it off, it's ready to assemble in the clock movement. You'll find that as simple as this winder is, that it is one of the most functional types of mainspring winders for open springs that you can obtain. Now, this one is made of cast brass, and probably so because it is very old. It has machined inner surface on it, but those are techniques that was personal preference of the manufacturer that made this. You'll find that many of these type winders is nothing more than a steel strap with a slot in the end, and that strap would pass here, down like this, over here, up and out, and have the pin with a hole in it. Many clockmakers make those from a steel strap about 1/8 of an inch thick and possibly about 1 inch wide. They're just as functional as this this brass one. I feel sure that one of this type would command quite a number of dollars, probably $10, $15 in 1987 cost. Again, it's simple. Having a little trouble getting the washer out of the way. Here we go. That's the clamp. Tighten it up so that it's not lost in the toolbox. This hole at that point has been drilled in there at some time, possibly for some special application. I doubt that hole was in there when the winding tool was originally built. Let's think about this situation and variations of it. We find that at least one manufacturer makes this with an extension on this end, a post out here, and a strap that goes across the top, this post being higher, a a strap across the top, which would be much like the plate, in the clock movement. That is a safety feature to keep the spring from coming out of the clamp or out of the tool as it's being wound. It has admirable qualities from a theoretical standpoint, but if you're careful to hold this situation in a hand grip, in a fist, in all of your work, there is no problem at all of that spring ever getting away or ever causing any physical damage. Now let me speak to another situation. That is winding this with a key. It's perfectly in order to wind this spring up with a key, but never, never, ever let it down with a key. The first time that I let this down in this illustration and it went zip, it turned 2 or 3 turns, I had the let down tool in my hand and I let it up just a little too much. If that had been a key, it would have beat your fingernails off of your fingers or broke your finger. I can assure you that that is one of the most dangerous things that there is with this type of winder. That is, letting a spring down with a key. Now, there is a let-down tool that is made, different from this. A set of these tools have 4 ends. The ends are different size. I don't particularly like this tool, even though it's nice, but every time I pick it up, I have to hunt the end. Is it this end or is it this end? Every time I lift it, it looks exactly the same. They're labeled. This one has a B, this one has a C. But when I pick this up, I have to rotate it and look for the B or the C or swap ends with it. And that becomes a nuisance as far as efficiency of working. The egg-shaped handle is good, works nice. The tool that I like most is about a 1-inch wooden dowel, approximately this length. Drill the end of it the size of the shank of a clock key, right into the end. Drill that hole about 1.5 inches deep. Then saw a slot crosswise in the end of the dowel that you may slip the dowel over the normal winding key. Now you have a tool that will fit, a single tool that will fit any clock by using the key that's appropriate to the clock. Slip the tool over the key. That gives you the friction handle to let this down. The tool can be made in a few minutes and is as functional as the best commercial tool you can buy. So, with the mainspring is not a terror if you have the winding tool and you have the understanding of how to use the tool. With a spring wound as this one is, it can be readily assembled into the clock in which it's intended to run, because the level of wind is approximately 3/4 of the way down from full wind. Now let's talk about another situation. Suppose this is an open spring clock movement and it has a hole end, in the end rather than a loop on the end. Now how do we cope with that situation? There's a number of ways of doing that. There is a little tool made that slips over this with a hook on it. And one could be made in your shop if you particularly like that idea. A little piece of tubing with a close connected hook, silver soldered on to the tubing, You could slip that over the tool, hook the whole end onto it, and proceed just as you do with this. A second situation is that you can lap the whole end of the spring up here and tie it with a turn or so of good strong iron binding wire. Still, a third situation, and probably the one that is the easiest, is you have a broken mainspring. Cut the rivet out, cut out this rivet, and save the loop end. Now when you have a whole end spring, take the loop end, which has been saved, slip it over the whole end spring, put a little screw and nut on it, and it becomes a loop end spring for this particular purpose. So as it goes, the spring is really not a tariff. That's purely an imaginary situation. This great wheel here, and this is something from the scrap box. The spring is an old one, but you would handle newer old springs alike, and you would ordinarily handle them with the great wheel from the movement in which they're intended. So be careful, hold tight, and you'll have great success.